Yeah. Saw that for most general coordinate transformation, this derivative operator do not transform like a expected object. Like we expect that this should transform as a covariant vector or covector, but because of some extra terms, it won't transform like that. Okay. So now let us go further. I will stop discussing the properties of tensors right now. Uh, uh, Again I will do that. Again I will come back to properties of tensor. But before that, let me uh, introduce the Lorentz transformations. Again, we already know what are Lorentz transformations. Okay. So we'll just introduce in this our new notation. Okay. So fine. So now we consider two coordinate system in Minkowski space. Okay. So consider x mu and x prime mu. Okay. And these two coordinate systems are related by Lorentz transformation. Okay. Now we'll define the Lorentz transformation in slightly different way. Okay. So the Lorentz transformation, the most general Lorentz transformation is defined as a linear transformation between x prime and unprime coordinate system. So it is given by this lambda mu nu x nu plus a mu, where lambda mu nus and a mus are constant. Okay, as it stands, mu runs from 0, 1 to 3. Okay, so remember, mu runs from 0, 1, 2, 3. Okay, so there are four numbers A0, A1, A2, A3, and then there are, as it stands, there are 16 numbers. Okay, lambda 0, 1, lambda 0, 0, etc. Okay, clear? But there is a restriction over this such that okay, such that there is no restriction over these numbers, but there is a restriction over this. We will see how. Okay, such that lambda mu alpha, okay, eta, which is metric, eta mu nu, okay, lambda nu beta is equal to eta alpha beta. So these lambdas must satisfy this. Okay. You will see that if lambda satisfy this, then this transformation leaves the space-time distance, the 4 distance square, unchanged. Okay. So why this comes, you will see that now. Okay. But there is no restriction over a mus. A mus are constants. And now you can see, suppose if lambdas are 0, suppose what are these a mus? Physically, can you think what are these a mus? If I set lambda equal to 0, okay, if I set lambda equal to 1, identity transformation, okay, then x mu, this will become for identity transformation, this will be just delta mu nu, right? Okay, it will be x prime mu equal to x mu plus a mu. These are, so these represent just translations. We'll see that again. This represents translations. Okay, and these are your familiar Lorentz transformations. Okay, okay, this is most general Lorentz transformation, although I should not say these are Lorentz transformation because these are actually Lorentz transformations and these represents translations. Okay, so uh, if if you want to use different name for this, you can say that these are inhomogeneous Lorentz transformations. These are inhomogeneous Lorentz transformations. Okay, clear? When amu's are zero, we have only lambda minus, and then we will say that it is a homogeneous Lorentz transformations. Okay, now we'll see why this condition is required. What this condition mean? It is the meaning of this condition. Okay, so let us start with ds square. Okay, what is ds square? Ds square is a 4 distance, okay, in Minkowski spacetime. Okay, remember, we can write this ds square in terms of metric and differentials, dx mu, dx mu. Okay, fine. Suppose if I define ds prime square in prime the 4 distance between 2 points, so there are q. Okay, I am taking the distance between them once in unprimed coordinate system and then in prime coordinate system. Okay, same point p and q. Okay, so in that case we should write eta mu nu, okay, dx prime mu and dx prime mu. Okay, clear? Okay, now you see there are differentials in this expression. The differentials are coming, hence you expect that if I substitute here, if I use this transformation to know what is dx prime mu, obviously it will not restrict a mu because a mu is a constant, so this will uh, it will not contribute to this differential. Okay, that's why there are no conditions on a mu. Fine. So this is the metric in prime coordinate system, and we want to show that this is equal to this. Okay, under this transformation, we will see that if this satisfies, then this is equal to this. Okay, let us see how. So ds prime square is equal to eta mu nu dx prime mu. What is dx prime mu? Dx prime mu is equal to, from here it will be lambda mu's are constant, it will be lambda mu alpha, okay, and dx alpha. Okay, clear? Because this is this quantity transform like, since there is an upper index, this quantity transform like contravariant vector. Okay. Hmm? What is this dx prime nu? Dx prime nu will be eta, this lambda nu beta dx beta. Okay, clear? So this is equal to eta mu nu lambda mu alpha lambda nu beta dx alpha and dx beta. Okay, there. Now this if this is equal to this, if ds square equal to ds prime square, what does it mean? It means that this quantity, I have to equate this quantity with this ds square. What is ds square? Ds square is eta mu nu dx mu dx nu, but these are summed indices, right? Okay, these are summed indices. I can even write here eta alpha beta dx alpha dx beta. So eta alpha beta dx alpha dx beta is equal to eta mu nu. I am equating this with this. Beta mu nu, lambda mu alpha, lambda mu beta, dx alpha, dx beta. Okay, this implies, now this happens for all dx alphas, dx betas, right? Because these are two arbitrary points. Okay, so this should happen for any differential. Okay, what does it mean? It means beta equal to beta mu nu lambda mu alpha, lambda mu beta. Okay, is it clear why this condition is required? So the Lorentz transformations are defined as linear transformation, okay, in 3+1 dimensional Minkowski spacetime, satisfying this criteria, satisfying this. Okay, note that AMUs I cannot fix by demanding the invariance of line element. So this dA square is called line element. Infinitesimal line element or four distance, infinitesimal four distance, anything you may call it. Okay. So the Lorentz transformations are linear transformations in 3+1 dimensional Minkowski spacetime, satisfying this equation, this relation. If you include AMU, then we call Lorentz transformation as inhomogeneous Lorentz transformation, or there is another name, is also called Poincare transformation. Okay. If AMUs are absent, then we call this as homogeneous Lorentz transformation or just Lorentz transformation. Okay, clear? For a moment, I will assume that AMU is absent, AMU is 0. We'll just deal with this homogeneous part. Is it clear? Now, I will rewrite this. Next page. So, eta alpha beta equal to lambda mu alpha eta mu nu lambda mu beta. Now, in the matrix notation, how should I write this? In the matrix notation, how should I write this? Remember how this lambda mu in general, so lambda mu alpha in the matrix notation will be like this: lambda 0 0, lambda 0 1, lambda 0 2, lambda 0 3, and lambda 1 0, lambda 1 1, lambda 1 2, lambda 1 3, lambda 2 0, lambda 2 1, lambda 2 2, lambda 2 3, and lambda 3 0, lambda 3 1, lambda 3 2, and lambda 3 3. Okay, so these are the entries of this matrix. Okay, so this is how the matrix lambda is defined. Okay, if this is the definition of matrix lambda, okay, then how should I write this in the matrix notation, this relation? If I denote matrix for this as eta, then what should I write? There will be eta, and what should I write? How to write this in the matrix notation? Where this, you see where this sum is coming, there is a summation over mu mu, there is a summation over nu nu, and right hand side alpha beta are free indices, because left hand side alpha, beta are free indices. Okay, so look at the position of this index mu. Okay, so if you compare with this, okay, this is a row index, right? This is row index, you see. Okay, rho is an eta mu nu. Okay, this is also row index and it is summed over. Okay? What does that mean? It means that in the matrix notation it will be lambda transpose eta lambda, right? Because lambda transpose, see, ideally what should have happened, it should, we should, the column of the first is some should be summed over row of the second. If you consider matrix multiplication a I j b j k, there is a sum over columns, right? Okay, so you have to, it should have come to, it should have been column index, that means the uh, further index. Okay, but it is coming as in the first lot. Okay, so if I consider this, if I consider this lambda mu alpha is lambda transpose alpha mu, right? Okay, so if I write like that, okay, then eta alpha beta lambda transpose alpha mu, okay, eta mu nu and lambda nu beta. Now everything is in place. Okay, now this is a proper matrix multiplication. So in the matrix notation it will be eta equal to lambda transpose eta lambda. Okay, in other words, the Lorentz transformations are defined by this. Okay, clear? Just a passing comment. In your usual 3D, usual 3 dimension, how you define rotation? How you define rotation? Rotation is the transformation which leaves distance unchanged. That means r dot r must be same as r prime dot r prime. Okay. From this, one can deduce that if I apply rotation to position vector, say r, okay, I will get vector r prime. Okay, and I demand that this is the transformation which satisfies this. Okay, we demand that the rotation is a transformation which satisfies this. It means that it implies that there is a condition over r. That condition is r transpose r equal to identity. That means R is orthogonal matrix. Okay, R is orthogonal matrix. Similarly, in Lorentz transformation, this lambda is orthogonal, satisfies this and this. If you are in doubt, then I can say that identity is a metric in uh, 3 dimensions, right? Okay, idea, what is this? Delta is, right? So this is the metric in 3 dimensions. So I could have written this as R transpose identity R equal to identity. It's same. Now you see the eta is the Lorentz transformation if it satisfies this. R is the rotation if it satisfies this. In any case, the space-time metric remains same. So the if you sandwich the space-time metric between the transformation, I should get back the space-time metric. This is what it means. In usual 3 dimension, you have only space. So you have only spatial metrics. Okay? Clear? So you can think with the analogy of rotation, the Lorentz transformation. Lorentz transformations are much more general than rotation, just rotation, as you can see. You will see later that this lambda also involves rotation. It involves rotation plus it involves something else, which we call as a boost. Okay? And we know what are the boost. Boost is this x goes to x1 goes to x as a function of x and t. Okay, t goes as a function of x and t, and y becomes y, z becomes z. These are our usual, we introduced in first two classes. Okay? Those are actually boosts. Apart from boost, there are rotation, which also leaves this metric unchanged. Okay? Note that although I have written this lambda mu alpha, although I have written the indices on lambda in this fashion, this lambda mu alpha, lambda mu alpha lambda, we should not think this as a 1-1 tensor. Okay, it is the matrix of transformation, right? It is not a tensor. If you go back to our early notation, the transformation between co-vector and contravariant and covariant vector is, you see, a j vj. Okay, this by itself is not a tensor. This is just a, this tells us how the bases are transformed. Bases have transformed. Okay, it may satisfy tensor properties, but uh, uh, as it stands, it's not. One should not think this as a tensor. It's just a transformation which connects two coordinate systems. Hmm? Clear? Okay. Okay. Sometime it it satisfy all. It sometimes it satisfy all the properties of tensor, but I should not call this as really a one tensor. Okay. Clear? Fine. Now, once we have the metric in place, once we have the Lorentz transformations, now we'll see. Okay, so I will just erase this statement. It is, I want to write something else. Hmm? Now the statement is the Lorentz transformations are the only non-singular coordinate transformations okay, that leaves okay ds square invariant or unchanged. Hmm? What is the meaning of this statement? Lorentz transformations are the only non-singular. Non-singular means what? If you consider the matrix of transformation and take its determinant, it should not be zero. Hmm? So these are the only non-singular coordinate transformation that leaves this d square invariant. So what we need to do? We have to consider most general coordinate transformation and impose the condition that ds square is unchanged. Okay, that must give me Lorentz transformation. No other, nothing other than that. So let us start. Okay. So so we demand that. So let us first consider the coordinate transformation x goes to x prime. Okay. So x mu goes to x prime mu. Under this coordinate transformation, your the metric in prime coordinate system, you can always write like this: eta alpha beta dx prime alpha dx prime beta. Okay, and that must be equal to your ds square. Okay, this is what we demand. Okay, clear? Note that this is, I should not assume this is from the beginning a Lorentz transformation. This is most general transformation. Okay. Now, under most general transformation, what would be your left hand side? Eta alpha beta. What should be dx prime alpha? Tell me what should be dx prime alpha under most general coordinate transformation. Dx prime alpha will be del x prime alpha, okay, del x mu, del x prime beta. Sorry, yeah, this is the only thing. Okay? Dx mu. So I will substitute this here. So eta alpha beta del x prime alpha del x mu, and then for this del x prime beta del x nu, okay, dx mu dx mu. Okay, this must be equal to ds square, which is eta mu nu dx mu dx mu. Okay, it means that eta mu nu equal to eta alpha beta del x prime alpha del x mu, your familiar tensor transformation rule for metric, del x prime beta by del x mu. Okay. Now suppose if I differentiate this, okay, differentiate this, okay, with del, okay, what I'm going to get if I differentiate this relation, say this relation, if I differentiate this, what I'm going to get on the left hand side? Hmm? If I differentiate this with respect to this, what I'm going to get on the left hand side? Pardon?
0.
0, because this is a constant, right? Every entry in this thing matrix is constant. Okay, so I will get 0 here, and on the right hand side, what I am going to get? Eta alpha beta del 2 x prime alpha by del x rho del x mu. Okay, del x prime beta by del x mu, plus eta alpha beta del 2 x prime beta at del x rho del x mu, and this term as it is. So del x prime mu divided by del x. So del x prime alpha and del x mu. Okay, clear? One. Suppose if I will get the similar equation if I interchange rho and mu from the beginning. Okay, so I will write this. Okay, so instead of writing mu here, I could have I can write rho eta rho nu as eta alpha beta del x prime alpha del x rho del x prime beta del x nu. There is no difference between this and this. Okay. Instead of writing mu here, I am writing rho. And now I will differentiate this by mu. but with del x mu. It is, I will get the similar equation with rho and mu interchanged. Correct? Okay. I will get the similar equation with rho and mu interchanged. No difference at all. No other difference. Okay. So I will get 0 equal to eta alpha beta del 2 x prime alpha del x mu del x rho del x prime beta del x nu plus eta alpha beta del 2 x prime beta del x rho is interchanged with mu, okay, del x prime alpha, and this mu is interchanged with rho, del x rho. This is equation number 2. Okay, clear? Now I will consider another relation, which is eta mu rho. Okay, eta, for instead of mu I will write rho here. Okay, so there will be rho here. It and then I will differentiate that relation with respect to del x mu. Okay, so I will get another equation. That equation can be obtained from this first by replacing mu with rho, by interchanging mu and rho. So I will get 0 equal to eta alpha beta del 2 x prime alpha by del x mu del x nu del x prime beta del x rho, okay, plus eta alpha beta del 2 x prime beta divided by del x, sorry, I think I have done something. I'm using this relation, so let me just erase this. So 0 equal to, I have to interchange here. Okay, so eta alpha beta del 2 x prime alpha del x nu del x mu del x prime beta del x rho, okay, plus eta alpha beta del 2 x prime beta divided by del x nu del x rho del x prime alpha del x mu. So this is my third. Okay, so now why I'm doing this? You see, if I add these first two and subtract third, what I'm going to get? If I add these first two and subtract from that the third relation. So let us write, okay, 0 equal to, so if I add, so I have to add this, so let me write first addition complete and then we will see. Okay, 0 equal to eta alpha beta, okay, eta alpha beta, and I will take eta alpha beta common. Okay, so because eta alpha beta is same in every term, del 2 x prime alpha divided by del x rho del x mu del x prime beta del x mu, okay, plus del 2 x prime beta del x rho del x mu del x prime alpha del x mu plus del 2 x prime alpha del x mu del x rho, okay, del x prime beta del x nu, okay, plus del 2 x prime beta divided by del x mu del x nu, okay, and del x prime alpha del x rho, okay, minus third equation, which was del 2x prime alpha divided by del x nu del x mu del x prime beta del x rho minus del 2x prime beta del x nu del x rho, okay, del x prime alpha del x mu. Okay, this entire thing is equal to 0. See what I'm doing, it looks messy, but it you can just add and subtract, right? Everything is there, you just combine these two and subtract from this, subtract third from it. Okay, but now you will see that if you combine, if you see the second term, okay, if you see the second term and the fourth term, the last term, they are same. You see, these are same because these are partials, so I can del x nu del x rho is same as del x rho del x nu. So this will go with this. Okay, these are same. Now which one else is same? This one. Okay, this and the no, this is not same. Okay, so yeah, my claim is that this one is same as this one. Can anyone tell me why? Del 2x prime beta del x mu del x nu. So let us consider these two terms. Okay, there is eta alpha beta del 2x prime beta del x mu del x nu del x prime alpha del x rho. Okay, minus this. Okay, so eta alpha beta del 2x prime alpha del x nu del x mu, okay, del x prime beta del x rho. Okay, my claim is that this is same as this one. Can anyone tell me? See, I
Metric is symmetric.
yeah, so I purposefully wrote in eta alpha beta here. Okay, they themselves will not cancel, but when you take into account this eta alpha beta is symmetric. So any symmetric matrix is come, and when you consider this next term, there is a beta alpha. I can interchange this. We have seen that yesterday. Okay, so in the this term, I can write beta here and alpha here. These two, this. Okay, any symmetric matrix and any arbitrary matrix. Okay, what is the this thing? Okay, which is same as eta alpha beta a beta alpha. Okay, right? If this is symmetric, but eta is always symmetric. Okay, so hence this third and this third term and fourth term will cancel. Okay, is clear? And what remains? What remains is this term, this, and this one. Okay, so 0 is equal to eta alpha beta. Okay, del 2, but this term is same as this one, just interchanging of mu rho as a partials will not create any difference, right? So it is twice eta alpha beta del 2 x prime alpha del x rho del x mu x prime beta and del x nu. Is it clear? Now tell me, what should, which term should I equate to 0? You see, eta alpha beta is not equal to 0 for arbitrary alpha and arbitrary beta. Obviously, it is not equal to 0 because it is as a matrix, it is an identity matrix. Okay, is it clear? So it's better way is to write this in the matrix form. In the matrix form, this 2 I can anyway erase because there is a 0 here, so there is no need of writing 2 here. Okay, so in the matrix notation, what would be the case? This is some kind of matrix. Okay, what will be the order of that matrix? Alpha beta are summed over. Okay, so if I write this as del 2x prime alpha del x rho del x mu then eta alpha beta del x prime beta del x nu. This is matrix version of this. You denote this as some kind of matrix. What kind of matrix will be? It will be third order. It will be like this: alpha rho mu, a alpha rho mu. Then this eta. Okay. So this will be some. What should I say? It's not three-dimensional. It is. Uh, it's it contains three indices, so it's like A, I, J, K. You are familiar with A, I, J. Okay, so it's A, I, J, K. In 4 dimension. Okay, so if you write this in the matrix notation, okay, it will be like some matrix A and alpha is summing over this alpha, so it is A transpose eta and some matrix B. Okay, it's which element? Alpha beta are summed over, so it's rho mu new element, rho mu new element. Okay, clear? Now this is equal to 0, then what should I conclude from this? This thing is equal to 0. You can either use this. I did this because it's simple. You can either use this, or you can, maybe if you can conclude from this condition, you can tell me what is the conclusion from this. You see, eta alpha beta as a matrix is not equal to 0. And is this equal to 0? What is our assumption? You go back. Lorentz transformations are the only non-singular, right? So non-singular means as a matrix its determinant is not equal to 0. Clear? Okay. And you see, this should hold for any indices. Okay. So if I say that this is 0, then this should be 0 for all betas and all nus. That means all the entries in this matrix will be 0. Okay, that means determinant is 0, which should not be the case. So I should not equate this to 0. I should not equate this to 0. What does it mean? It means that del 2x prime alpha divided by del x rho del x mu is 0. Okay, it means that your x prime alpha must relate to unprimed x by linear transformation, and that linear transformation I am calling as lambda alpha beta x beta plus, obviously 0 degree term will be there, right? This is the first degree term, so it will be some mu. Okay. Moreover, when you substitute this here in reverse way, now we will do in reverse way. Okay, so from this we conclude this, but still it does not prove that this is Lorentz transformation, because for Lorentz transformation this must satisfy this condition, right? Okay, this lambdas must satisfy this condition. Okay, this tells us that this is a linear transformation. Okay, now if you take this and substitute here, okay, use here, okay, okay, you will get that condition automatically as we did in our previous case. Okay, here we did, right? Okay, so indeed these are the Lorentz transformations. Okay, so you see that the Lorentz transformations are the only non-singular transformations which takes x to x prime, okay, and which leaves ds square invariant. Is it clear? Hmm? Note that I have not used any detailed form of lambda mu nu. Okay, this matrix I have not used any of this entry. Okay, although we have derived it already. Okay, first to first. So this is without using the exact knowledge of these entries. Hmm? The result which I am drawing. Okay, clear? So from now onwards, we take coordinate transformation as a Lorentz coordinate transformation or Lorentz transformation. We think coordinate transformation as a Lorentz transformation. Okay, is it clear? Any question till now?
Sir, that A transpose eta B.
Hmm. I have just written in the matrix notation. Okay, so B matrix is non-zero, eta is non-zero matrix. Okay, so what is eta? Eta is 1 minus 1 minus 1 minus 1. It is non-zero matrix, right? B by non-singular nature, it should not be zero, right? Or at least its determinant should not be zero. Then only thing is that this thing is should be zero. What is this? This. Is it clear? What was your question? This is what you are asking, right?
Sir, just like lambda transpose eta lambda equal to eta, we
Hmm.
can say uh, about the Lorentz transformation. So what we can say about this A
No,
transpose
no, no.
eta
This is
B
not. No,
on
no. This
this
is not a
equal to
rule.
zero?
I
What is
just
that A transpose at B?
no, no. I denoted it. It carries no physical meaning. I just for your convenience, purpose of writing this is just to emphasize that see this is equal to zero. Okay, so either all of them should be zero, or at least one of them is zero, or at least two of them is zero, right? Okay, so all of them should not be zero because eta is see this should hold for all indices. Okay, for that means for all alpha, all beta, anyway alpha beta is summed over, so it should hold for all indices. That means all values of rho, mu and nu. Okay, if this is zero for all values of rho, mu, nu, then which of these three terms we should equate to zero? That is the question. Hmm? Okay. I should not equate this to zero. I should not equate this to zero. I should equate only this to zero. That is, so I have written this just in the matrix form, just to emphasize that matrix B is non-singular, eta matrix is non-singular. Okay, so this must be zero. That is what it carries no physical meaning. It is a notation. Hmm? This is different. This is coming from the invariance of the line element. Hmm? Okay. You can say that this means this. But don't think this as something, this is just to simplify. Okay, good. So now I will go back again to uh, tensors. Okay, but before even doing that, okay, let me list certain properties of Lorentz transformations. Okay, so we have seen that the Lorentz transformations are linear transformation in 3 plus 1 dimensional Minkowski space which satisfy this condition. Okay, from this condition alone, what we find? Okay, so we have lambda transpose eta lambda equal to eta. Hmm? Okay, so firstly, your most general Lorentz transformation or inhomogeneous Lorentz transformations are given by this. Okay, so let us put a mu equal to 0. Okay, for a simplicity. Then my homogeneous Lorentz transformation or just Lorentz transformations are defined by this transformation. Okay, where lambda satisfy this condition. Okay, now tell me, if I take the determinant of this, what is going to happen if I take determinant on both sides? Then lambda transpose eta lambda equal to determinant of eta. Okay, what should be the answer?
Determinant of lambda should be equal to 1 plus minus 1.
Yeah, so determinant of a b c is determinant of a into determinant of b into determinant of c. We don't need to calculate determinant of eta. Determinant of eta anyway cancels out. Okay, so determinant of lambda transpose and determinant of lambda equal to 1. Okay, it means determinant of lambda transpose is same as determinant of lambda, right? So determinant of lambda square equal to 1. It implies that determinant of lambda equal to plus or minus 1, right? So the Lorentz transformations falls into two categories. Okay, that is not the only category, but it we have here just two categories. One, the Lorentz transformation whose determinant equal to 1, and the Lorentz transformation whose determinant equal to minus 1. Okay, Lorentz transformations having determinant equal to 1 are known as proper Lorentz transformation. Lorentz transformations having determinant equal to 1 minus 1 or improper Lorentz transformation. Okay, clear? Okay. Now you think Lorentz transformation physically. Can I have, suppose if I apply a Lorentz transformation to some coordinate system, okay, that means I have a frame, okay, which which relate to another frame which moves with the constant velocity, say for example boost. Okay, I can take that velocity to be 0 also. That means I have two identical frame just. Okay, that means I have an identity Lorentz transformation, correct? I have the identity transformation is a Lorentz transformation, right? Because I can, in the our earlier Lorentz transformation which we derived in our first two classes, I can put v equal to 0 there. which is just the identity transformation. Okay? But it is a Lorentz transformation, right? I will get, if you write four-dimensional matrix for that, I will get four-dimensional identity matrix. And four-dimensional identity matrix obviously satisfy this criteria, right? Okay. Hence, this four-dimensional identity matrix is a Lorentz transformation. Okay. Now, if I start from identity transformation and if I keep on giving boosts, okay, which kind of Lorentz transformations I'm going to get? You understand the question? I have an identity transformation, that means V equal to 0. You think only about your only with regard to boosts. Okay. Although Lorentz transformation contains much more than boost, okay, you think first in terms of boosts. Okay. If I start from identity, okay, and if I keep on giving, I consider a frame which moves with, say, velocity v1, then I consider a frame which moves with velocity v2, and so on. So I will get some succession of Lorentz transformation, right? Okay. So all those Lorentz transformations are coming from identity. I'm giving boost to identity Lorentz transformation or identity frame. Okay. From identity, I'm moving slightly away from the identity. Suppose if I give small velocity, okay, small velocity, okay. So this frame uh, and another frame will be differ by this, okay. Then I will keep on giving the small velocity successively. So what kind of, where we will land up? If I pick up any finite Lorentz transformation, okay, which ultimately relate to original frame by velocity v, okay, this is the Lorentz transformation which takes the frame which represents a frame which moves with velocity v with your original frame. If I apply successive boosts, right? So there must be some relation between the coordinates x and coordinate x prime here. Okay, and that relation is given by this lambda. Okay, what kind of lambda will we get? This one or this one? What do you think? Or both? You understand the question? I'm starting from identity transformation. I give successive boosts, infinitesimal boosts, and I obtain a finite transformation, wherein the frame represented by that transformation is the inertial frame which moves with the velocity v related to original frame. Okay, then I have a Lorentz transformation lambda, which we have obtained by succession of Lorentz transformation starting from the identity, right? So my question is, this lambda, if I calculate determinant of this lambda, whether it will be plus, what will, I have told you everything. You can answer from that. You can answer from that information. I told you that identity is a Lorentz transformation. What is the determinant of identity? Just one. Agree? And I'm starting my Lorentz transformation and reaching to this Lorentz transformation. I'm starting with this frame and I'm reaching to this frame. Okay, by succession, continuously, I'm going. Okay, so now any continuous transformation, okay, will not take me from determinant plus one to determinant minus one, right? Because Suppose if this Lorentz transformation has determinant -1, what does it mean? It means that by slowly reversing the Lorentz transformation, I should get my original frame. Okay, but the original frame is the identity Lorentz transformation, which is this. Okay, but if I start from this and if I continuously reverse the Lorentz transformation, I will get minus identity. Right? Okay, is it clear? Okay. So the Lorentz transformation, which starts from which is continuously connected to identity, will have determinant +1. Okay. In other words, suppose if I think this Lorentz transformation as a function of some parameter, we know what that parameter is. It is a velocity. Apart from velocity, there will be other things, but velocity, as far as boost is concerned, velocity is the parameter. Okay, and if suppose if I expand this, okay, suppose if I consider delta v, and I suppose if I expand by Taylor series near identity, what I am going to get? Identity matrix plus some, say, lambda tilde, okay, some infinitesimal part, okay, near identity. It's a Taylor expansion. There will be other terms, but since delta v is small, I'm suppressing those terms. Clear? Now, if you take delta v to be 0, this part will go, this will remain, okay, whose determinant is +1. You understand? Okay. So, any transformation which continuously relate to identity must have determinant +1. Continuity is important. Okay, because if I have a transformation which is having determinant -1, then I will never reach to identity. I will never reach to identity. I will reach to minus identity. Okay. So this is one thing. So I have a Lorentz transformations. In general, the Lorentz transformation will have determinant +1 or -1. +1 are called proper Lorentz transformation, and -1 are called improper Lorentz transformation. The Lorentz transformation which relate to identity continuously, okay, must have determinant +1. Hmm? Now, so this is first point. Second point is you start from this lambda transpose eta lambda, and now I will again write in tensor in component form. Okay, in the component form, what will be this? It will be, we have done it before, lambda alpha mu, okay, eta alpha beta, lambda beta mu equal to eta mu nu. Okay. Suppose if I consider on the right hand side, you put mu equal to 0 equal to nu, zeroth component. Okay, so eta 0 0 equal to what? Lambda alpha mu equal to 0, eta beta let us complete this sum. So lambda, first you put 0 here, 0, lambda 0 0, eta 0 0, because if alpha equal to 0, beta must be 0. Okay. Then here it will be lambda 0 0, right, plus, okay, lambda, put alpha is I, alpha can be 0 or I, right, either time index or spatial index. So it will be I0, eta I, then beta can take value j, right? Then lambda j 0. Okay, finished. So what is eta 00? It is 1. So there will be lambda 00 square. Okay, what will be eta ij? It is minus delta ij. So it will be minus lambda I0 and lambda I0, right? So this is lambda 00 square minus lambda I0 square. Okay, this is equal to eta 00. But what is eta 00? Eta 00 is 1. Okay, hence lambda 00 square must be equal to 1 plus lambda I0 square. What does it mean? It means that lambda 00 square is always greater than or equal to 1, because these are the square of some quantity. Okay, so it is always greater than 1. It implies that lambda 00 is either greater than 1 or lambda 00 is less than minus 1. Okay, is it clear? Okay, Lorentz transformations with lambda 00 greater than 1 are known as orthochronous. Orthochronous Lorentz transformation. What it says, what they represent, it represents the Lorentz transformation which takes your time coordinate in future. Okay, okay, which takes your time coordinate in future. So it will give me the future time. If I apply this to t, okay, I will get t prime which is greater than t. Okay, so it represents the Lorentz transformation which takes your time coordinate in future. And Lorentz transformations with lambda 00 less than or equal to minus 1 are called non-orthochronous Lorentz transformation. Okay, this is the time 12:09. Okay, so I will take till 12:15 or 12:20. Is it clear? Good. Okay. So we have 4 classifications, okay, of Lorentz transformation. So lambda, there are 4 classifications. Okay, so you have proper, improper, okay, orthochronous, non-orthochronous. So I should write proper, orthochronous, okay, improper, non-orthochronous. Okay, so you have this. Okay, so Lorentz transformation which are proper orthochronous, proper non-orthochronous. It can be improper orthochronous, improper non-orthochronous. Okay, so you have proper orthochronous, okay, improper orthochronous, improper non-orthochronous, okay, and proper non-orthochronous. So you have 4 divisions. Okay, so proper orthochronous. Okay, so let me erase this diagram and write. I will represent them by sets. Okay, so Lorentz transformations. Okay, I will consider a set of Lorentz transformations denoted by this symbol. Okay, this is the set of Lorentz transformations. Okay, satisfying determinant of lambda equal to 1 and lambda 0 is greater than or equal to 1. This is one set. Okay, then I will have a set of Lorentz transformation whose determinant is 1 but whose lambda 0 component is less than -1. So it is a set of Lorentz transformation whose determinant is 1 but whose lambda 0 component is less than -1. Okay. Then I will have a Lorentz transformation whose determinant is -1 but 0 component is greater than 1. And I have a Lorentz transformation whose determinant is less than 1 as well as determinant is -1 as well as lambda 0 is less than -1. Okay, so any Lorentz transformation falls either in these categories, in these four categories, either of these. It's called proper orthochronous, it's called proper non-orthochronous, this is improper orthochronous, and this is improper non-orthochronous. Okay, is it clear? Now one can show, we'll do this at the latter part of this course or in the next semester. But you will be certainly doing this in your MMP2 group theory part. Okay. One can show that the Lorentz transformations, set of all Lorentz transformations form a group. Okay. This L plus up is a subgroup. You'll see this. You'll be studying this in your MMP2 course. Subgroup of not this particular group, not the Lorentz group, but in general, what is group you will be studying. And at the end of this course or in next semester, we will see detailed structure of Lorentz group. Okay, L plus up is a subgroup of lambda, while these three are not subgroup of lambda. They do not form subgroup. Okay, so this is the subgroup. Okay, this nomenclature is not important right now. Okay, this is just for your information. Later on, it will play a crucial role. At this moment, it's not important. But it is important to understand that any Lorentz transformation falls into these categories, either in these, either one of them. Okay. Now, just by looking at this classification, one can see that the following. Okay. you consider a Lorentz transformation, okay, let lambda be element of L plus up, L plus upset. That means determinant of lambda is 1 and determinant of and lambda 0 0 is greater than 1. Okay, and let us consider lambda bar be element of L plus down. Okay, can I write this lambda bar in terms of this lambda? What is this L plus lambda denotes? It means the determinant of lambda bar is equal to 1 and lambda bar 0 0 is less than minus 1. Remember, this is one Lorentz transformation. This lambda bar represents another Lorentz transformation. Okay, this is the Lorentz transformation satisfying these properties. Now, can I write this lambda bar by some matrix multiplied by this? What is lambda? Lambda is the matrix which has determinant plus 1 and lambda 0 0 minus 1. So now, if I consider the following matrix, if I consider minus 1 plus 1 plus 1 plus 1, okay, and rest of the entries are zeros, and if I multiply this to lambda, okay, this lambda, then I am bound to get this kind of matrix. Agree? Okay, I'm bound to get a matrix whose determinant is plus 1. Okay, sorry, whose determinant let me see, am I doing some mistake? Just a minute. So I should impact yeah. So if I consider this matrix, not this one, suppose if I consider minus 1, okay, then I can obtain what is the determinant of this. Determinant of this will be plus 1. Okay, determinant of this will be plus 1. Okay, so determinant of lambda bar will be plus 1. This is satisfied. Okay, and because of this minus 1, and it is given that lambda 0 0 is greater than 1 and this is minus 1, therefore lambda bar 0 0 will be less than minus 1, less than or equal to minus 1. Okay, so this is satisfied. So any lambda bar belonging to this can be written as this matrix multiplied by suitable lambda in proper orthogonal transformations. Okay, so you have proper orthogonal transformation. From that, we can generate this element of L plus minus. Now, suppose your lambda bar belongs to, say, uh, uh, L minus up, L minus up. So it will have determinant of lambda bar equal to minus 1 and lambda 0 0 is greater than 1. Okay. Can I write this lambda bar similar to this? I want to write this lambda bar as something into lambda. Okay. So I want determinant to be minus 1. Okay. So let me write, but lambda 0, 0 should be greater than 1, right? So here this has a property that lambda 0, 0 is greater than 1. That means this entry must be 1. Okay, and all entries must be minus 1, minus 1, minus 1, right? Okay. So let me call this one as lambda pt. Okay, this symbol pt. Let me call this one as lambda p. Okay, now I will consider lambda bar which belongs to L minus down. Okay, you have L plus up, L plus down, L minus up, L minus down. Okay, so L minus down means it has determinant equal to minus 1 and lambda 0, 0 less than minus 1. So now I can write as minus 1 plus 1 plus 1 plus 1, right? And times lambda. Okay, you can see that its determinant is minus 1 and its lambda 0, 0 is less than minus 1, because this lambda 0, 0 is greater than 1. So lambda bar 0, 0 will be less than minus 1 because of this. I will call this as lambda t. This matrix, you can think physically, is the matrix which changes the sign of spatial coordinate. If you act this lambda p on, say, x, what is going to happen? X0 will go to x0, right? You can see x0 column. So lambda p, which was 1 minus 1 minus 1, 1 minus 1 minus 1 minus 1, and it acts on x0, x1, x2, x3. What is going to happen? It will give me x0. This will give me minus x1. This will give me minus x2. This will give me minus x3. So this represents parity. Okay. Let us concentrate on this. Hmm? If I act that matrix on this column vector, there is a minus, plus, plus, plus. What it gives me? It gives me minus here and plus, plus, plus. So this changes the sign of time. Okay, so it is, we'll see later that this will be denoted by time reversal. Okay, and this analogously you can say it is parity and time reversal. Both. Okay, clear? Okay, so the Lorentz transformation can be broken up into 4 pieces. By using one piece, that is proper orthogonal transformation, one can generate all other Lorentz transformations. Okay, by multiplying them, by multiplying proper Lorentz transformation by either parity or time reversal. Okay, but these are, you see, these are not continuous transformations. These or these. These are not continuous Lorentz transformation. They are discrete. Okay, you are changing the sign of t to minus t or vector x to minus x. Okay, we'll come to this in the latter part of this course. Okay, what is the time? Yeah, I think you have a class. You have class at 12:30, right? Hello?
Yes, sir.
Yes, sir.
Okay. So we'll stop here. And but is it okay if I take at 2:30 today? Or you will be exhausted? I want to take for 1 hour. Is it okay if I take after, 1 hour in the afternoon?
Okay, sir.
If there is any problem, you can tell me. I will not take. If there is no problem, then I will take. If you are willing to join, then I will take. Because I
Yes,
don't
sir.
want to disrupt the flow of this. I want to finish something. Okay. So we can take. But if there is any problem, then you can tell me. Then I will not take. There is nothing in the afternoon, right?
No, sir.
No editorial.
No, sir. Not scheduled.
Okay. Then what time should I take? 3 o'clock or 2:30? Tell me the time.
So 2:30 is fine. Yes.
3 o'clock
2:30 is fine, I will.
for all, or do you want some relaxation from, because there is a lecture after this? So
Sir, it will be fine.
so 2:30. Is it okay?
Okay, sir.
So okay. So we'll meet at 2:30. Okay. Again, I will arrange the meeting. Okay? And I will meet at 2:30. Is it clear?